So we are on chapter 4. What we learned so far in 4.1, we learned that we have two types of variables. A random variable denoted by x is either discrete, countable, or it is continuous. It takes on some values on an interval. In 4.2, we're going to talk about one of the most important discrete distribution that we call binomial distribution. So let us officially define a binomial distribution. A binomial experiment is a probability experiment that satisfies these conditions. First, the experiment has a fixed number of tries where each trial is independent of the other trials. So when you are looking at an example or a question, you have to have independent condition between the trials. The second condition, there are only two possible outcomes, no more than two. Each outcome can be classified as a success, S, or as a failure, F. The third condition says the probability of a success is the same for each trial. And fourth, the random variable x counts the number of successful trials in your experiment. So your x might be no success. Your x might be just one success. Your x might be two successes in your experiment. Your x might be 3, and so on. So you can actually list the number of successful trials in your experiment. Okay, notation for binomial experiments. N is the number of trials. P, the probability of success in a single trial. Q, the probability of failure in a single trial. What's the connection? What's the relation between P and Q? Q, the probability of failure in a single trial is equal to 1 minus P, which is the probability of success in a single trial. And X is the random variable, represents a count of the number of successes in n trials. So X can be either 0, no success, 1 success, or 2 successes, or 3 successes, and it stops at n. What is n? N is the number of trials. On the next page, we have an example. So here, your goal is to identify and understand binomial experiments. So first of all, the question says determine whether the experiment is a binomial experiment. If it is a binomial experiment, then identify n, p, q, and list the possible values of the random variable x. If not, explain why. So the first one says a certain surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. Okay, the second one says, a jar contains 5 red marbles and 9 blue marbles and 6 green marbles. You randomly select 3 marbles from the jar without replacement. Remember from chapter 3, without replacement, it means that these are dependent. You get dependent trials. So does it satisfy the conditions of a binomial experiment? Take a look at your binomial experiment. Binomial experiment must satisfy these 4 conditions. First of all, the first one says each trial is independent. So it conflicts with the first condition and it is not a binomial distribution. For the first one, here we have a binomial experiment. Why is that? Because you have patients, they are independent from each other. P, the chance of success is 85%. How many patients in total? 8, so N is 8. What is Q? The probability of failure, 1 minus 85%, which is 15%. What about your X values? X can be 0, X can be 1, X can be 2, X can be 3, X can be 8. You have to list all of them. So in previous page, look at the last condition, 4. The random variable X counts the number of successful trials. You either have no success in your trials, 0, or you have 1 success, or you have 2 successes, or 3 successes, or 4. You don't know. So you have to list all of them. So look at our example. We are listing all the possibilities for our X. X can be 0, no success in the surgery. X can be 1, it means that 1 surgery was successful, one patient, or 2 of them. Or,
all the way to A, right?
Yes, very good. Or
perfect,
all of the patients had successful surgery. Perfect. Another example, finding a binomial probability using technology. So the result of a recent survey indicates that 67% of US adults consider air conditioning a necessity. Okay, 67%. It seems like we have a binomial experiment and this is our P, the probability of success, 0.67. You randomly select 100 adults. So your N is 100. What is the probability that exactly 75 adults consider air conditioning a necessity? So the question says, what is the probability that exactly 75 adults consider air conditioning a necessity? How do we calculate this probability using binomial distribution? Okay, perfect. Guys, we have to follow the instruction for binomial distribution. Please open your Canvas. Calculator instruction. So let me share my screen with you. Go to Canvas, calculator instructions. Perfect. Now we're looking for the binomial distribution. Okay, perfect. Calculating probabilities with binomial distribution. The first one, the first instruction is when the question says exactly X successes in your experiment. So turn on your calculator, press second, then vars, then select 0 binomial PDF. Guys, this is very important. It is binomial PDF, not binomial CDF. We're going to talk about binomial CDF later. And press enter. Enter the number of trials, N, then probability P, then the number of successes. This is the instruction. Let's get back to our example. Okay. So, second was 0, which is binomial PDF probability distribution function. Enter. Then you need to enter N, P, and X. What is our N in this case? N is 100. The total number of trials. P, the success, is 0.67. What is my X? It says exactly 75. So 75 goes here. If you're using TI-83, you can use parentheses and put 100.67 and 75. Enter. The outcome must be equals to 2%. 0.02. So the probability that exactly 75 adults consider air conditioning a necessity is going to be just 2%. So in this example, we learned that if the question says exactly, guys, this is the keyword to use PDF. So exactly, it means that you have to use binomial PDF. Okay, perfect. Another example. So in this example, you have about 60% of cancer survivors are ages 65 years old and older. You randomly select six cancer survivors and ask them whether they are 65 years of age or older. Question says, construct a probability distribution function for the random variable x, then graph the distribution. Perfect. Okay, so what do we have here? First of all, this guy is a binomial distribution. P is 60%, N is equal to 6, and since X is not given, it means that X can be 0, or 1, or 2, or 3, or 4, or 5, at most 6. The probability that X is equal to 0 is going to be very small. The probability that X is equal to 1 is 3%, 4%. The probability that X is equal to 2, it's 14%. The probability that X is equal to 3 is 28%. The probability that X is equal to 4 is actually 0.31 or 31%. The probability that X is equal to 5 is almost 19%. And finally, the probability that X is equal to 6 is going to be 0.047 or just 5%. We learned how to graph a probability distribution. On horizontal axis, you list all possible X values. X values, X can be 0, X can be 1, X can be 2, 3, 4, 5, 6. On the vertical axis, you have your probabilities, P of X. The probability that X is equal to 0, as you can see, is very small. So our graph stops here. It's a very small bar. The probability that X is equal to 1, it's almost 4%. So the graph, the bar stops here. And so on. This is our probability distribution function. So when you have a binomial distribution, you can find the mean of binomial distribution, N times P. You can find the variance, sigma squared, NPQ, and you can take square root of your variance and define your standard deviation. So 3 important formulas. One example to clarify this, in Pittsburgh, Pennsylvania, about 56% of the days, okay, 56%, so it means that your P is 0.56 days in a year are cloudy. Find the mean, variance, and standard deviation for the number of cloudy days during the month of June. Okay, month of June. How many days are in June? What is my N? N, or the number of days in June, is going to be 30. So the mean is N times P, 30 times 0.56. Variance is NPQ, 30 times 0.56 times 0.44. And my standard deviation is square root of 30 times 0.56 times 0.44. If you do the calculation, your mean is 16.8, your standard deviation is equal to 2.7. Guys, take a minute or two. I'm going to explain one last thing for you.
Professor, I had one question for you.
Go ahead.
How did we get the 44?
So what's the relation between P and Q? Q is 1 minus P. Q is 1 minus P is 56%. 1 minus 56% is 0.44.
Perfect. Thank you very much.
Make sense for everyone? Perfect. Bethany, your previous example, this one? Okay, perfect. Sure, definitely. And one last thing, if you go to your Canvas, I posted a picture here for CDF. So we talked about PDF. PDF was pretty easy to work with. Now CDF, so perfect. When it comes to binomial distribution, if the question says, find the probability of exactly, you use PDF function. If it says, find the probability that X is less than or equals to. Guys, listen carefully. Find the probability that X is less than equals to a number. Instead of using PDF, you have to use CDF. If the question says, find the probability that X is just less than, there is no equality here, less than K, you have to use binomial CDF, and instead of writing K, you have to use K minus 1. if the question says, find the probability that x is greater than k, it is 1 minus binomial CDF. If the question says, find the probability that x is greater than or equals to k, it is 1 minus binomial CDF, and you have to subtract 1 from k as well. Okay, guys, let's have 5 minutes, 10 minutes break. We get back and start working our group activity.